Okay, let's start with the lecture today. Today we're going to talk about first we'll talk a little bit about HTTP as an example of an application layer protocol. Then we'll look at a little bit on issues involved with the web, issues like caching, and then a related topic which is content delivery networks. Once we're done with that, then we'll look at P2P networks. So your first programming assignment is ready. I'll make sure that the TA puts it up today on the website. It has to it deals with providing an overlay service that can let you do things like instant messaging or other communication between different applications or services, and that programming assignment will reinforce what we spoke about in the last lecture of the importance of decoupling location with identity in any naming system of a network. Okay, so let's start with yeah. You have 3 weeks for the programming assignment. So we are all familiar with the web and HTTP and HTML. We will get into more details of HTTP today. So as we all know that a web page consists of different objects. So when you're looking at a web page, it'll have an HTML file, maybe some images, an applet, music file, whatever. So when you're going to any web page, suppose you go to www.columbia.edu, the default HTML file that is given to your browser is index.html. That's the base HTML file, and that will include several of these referenced objects. So on the web page you'll have some text, you'll have maybe frames, so you'll have different HTML files that will be downloaded, you'll have an image of Columbia, lots of stuff would be there. Each of those objects is identified by a different URL, and HTTP defines how these URLs or objects are transferred between a server and a client, and we'll see what sorts of performance issues creep in deciding this protocol. So on the home page of Columbia, you might have some picture. So pic.gif. This is an object, and how is this object going to be transferred? That HTTP decides, and different versions of HTTP do it differently, and they can have significant performance issues with the way things are implemented. So again, overview, we are all familiar with this. You have different web clients, browsers running on different operating systems, different versions of these browsers. They all talk to a standard server. The server also could be an Apache server, an IIS server, Netscape server. But all the clients and servers follow the same protocol, which is HTTP. So the client browser will request these web objects, and the server responds to these web objects. The first implementation of HTTP which defined this message exchange was HTTP 1.0. The RFC is 1945. Then the next version came along, HTTP 1.1. RFC is 2068. We look at what's the basic architecture of HTTP and how 1.0 and 1.1 differ. So HTTP is used to transmit or transfer these objects of files between clients and servers. So first of all, it needs to use a reliable transport protocol, because if you miss bits of files, you cannot recreate the file exactly, you cannot recreate an image exactly. And the assumption behind HTTP is that everything has to be transferred reliably. So HTTP uses TCP, it never uses UDP. The server in HTTP is stateless. So HTTP server maintains no information about past client requests. Now, this thing you have to take with a pinch of salt. We'll see how servers do manage to keep some state, and how that state is kept and used. So that's sort of not something which is done by the HTTP server. HTTP server itself is stateless, but the way you build web servers, you can create the notion of having some state, maintaining some state, and using and exploiting that state. Now, as we saw in the last lecture, that protocols that maintain state are complex. You have these hard state protocols, soft state protocols. They have performance issues, they have reliability issues, they have security issues. So as far as possible in the network, you try to come up with stateless protocols which don't need to maintain any prior history or prior state for effective functioning. Because once you start maintaining state, the protocol or the architecture is not very scalable, and it can get into situations which can't be resolved easily. So HTTP server is stateless. So every connection that you make is a new connection in as far as the server is concerned. It maintains no history. So HTTP uses TCP. Your client will initiate a TCP connection to a well-defined port, which is 80. Server accepts the TCP connection from the client, and over this TCP connection, your HTTP messages are exchanged. Once you're done with the message, the TCP connection is closed. So what are the kinds of HTTP connections? There is non-persistent HTTP, which was the original design, which was part of HTTP 1.0. In non-persistent HTTP, at most one object is sent over one TCP connection. So if your web page has your index.html contains one text file and 10 different images, then a server and client which are talking to each other using HTTP 1.0 would need 10 separate TCP connections to transfer these objects. Now a TCP connection, there is a connection overhead, there is handshaking going on, so there is latency involved in creating a TCP connection. Also, for every connection you have to maintain state at the transport layer in the operating system. So creating a new TCP connection for every object is not a good idea. So before HTTP 1.0, before people fix HTTP 1.0, browsers sort of try to get to do a workaround this problem. We'll see how, in the next slide I'll show what the exact problem is and how browsers try to work it around. People notice that the 1.0 architecture is not very good. So in 1.1, persistent HTTP was introduced. In persistent HTTP, multiple objects can be sent over a single TCP connection. So if you have 10 objects that need to be transferred for a web page, you don't need to create 10 different connections. There's a single TCP socket over which you'll transfer everything. And even in persistent, there are variations. We'll look at that. So non-persistent HTTP, This is the process. The client will initiate a TCP connection to the HTTP server. HTTP server will accept the connection and will send a response message back which contains the requested object. So the requested object was the home page of some department, home.index. So when the HTTP client sends this request, the response message will come back with this base object, the base file. Now this base file will have embedded references to different URLs. It will find maybe 10 reference JPEG images in that page. So the page that was initially transferred was only text, but that text contained references to different images. So in non-persistent HTTP, as soon as you receive the first base file, you close the TCP connection, and then your browser will pass the base file and will see that there are 10 more objects that it needs to download to display the web page correctly. So it will repeat the steps 1 to 5 for each of these 10 images. Yeah.
Suppose the images are large enough for it to take over the handshaking task that it takes when everybody uses HTTP 1.0. If you have image files that are large enough, that the transmission time is significantly larger than what the handshake is.
Yeah.
If you're transmitting them, each of them in individual connections, it should get done faster than if you just transfer them at the same time.
Sorry, can you repeat the question? If your image is large enough.
Real large images.
Yeah.
That the handshaking, that the time it takes to do the handshake
Yeah.
will be ignored. Then would it make more sense for you to do HTTP 1.0 instead of 1.1, which is going to...
No. It still doesn't make sense to do 1.0. See, so what you're saying is that now here we're doing response time modeling, how long it takes to transmit a particular object, right? So this initial time that is the TCP handshake, that is the overhead for every transfer. Now what you're saying is that this is the time it takes to transmit the file. So what you're saying is that this is very large, so that you can ignore this. But still, why do you want to add that overhead for every transfer?
You have 10 images, and you have to do one connection for each image.
Right.
When you do them simultaneously, the same connection, or you open one, close it, open the other one, close it.
So open one, close is the way 1.0 does it.
You open them sequentially, or you open them
Sequentially, yeah.
So you open them parallel.
Yeah, so HTTP 1.0, you have to do things sequentially. But so the clients, the people who are writing browsers saw this problem, that there is this long wait. You have to get one object, close the connection, get the next object, close the connection. So browsers started doing parallel downloads. So browsers started creating 4, I think the number was 4 or 5 simultaneous downloads from a server. So in the previous example, you go to the web page and the HTML file tells you that there are 10 more objects, 10 more images that need to be downloaded. The idea behind HTTP 1.0 was that each browser will download one image, close the connection, then download the next image, close the connection. But what browsers started doing was, when they realized that they have 10 of these images to download, they opened up 4 parallel TCP connections, and on each connection a different image was being downloaded. So what that did was, it sort of speeded up the download times as perceived by a client, because now you have 4 parallel downloads going on. You don't have to wait for one. to start the next one. Yeah.
But then for parallel download, you can have four different URLs, but if you have the same URL, you want to start from the same point?
No, I mean you're downloading different images, right? Each image is a URL of its own. Each image is an object of its own. So you're in the 4 parallel connections, you're downloading different objects. So that what the browsers did made things better for the client. But did it create any problem at the server? Yeah. Server got overloaded with connections. So now the server is expecting sequentially these connections. It's getting parallel connections. So it started running out of sockets or connections very quickly. So clients could change the way things work by sort of a hack, but that made things worse for the server. So HTTP 1.1 came up with an architecture which made things better for both client and server. So in persistent HTTP, a server will leave connection open after sending a response. For a certain timeout period, the socket is left open. Now, I wish there was a telnet client or an SSH client on this machine. We could have shown that to you. In persistent HTTP, the server will leave the connection open after sending the initial response, and subsequent HTTP messages are sent over the same socket. But this socket is not left open or hanging for a very long time. The timeout period is relatively short. Even in persistent HTTP, there are 2 ways of doing things. One is without pipelining and the other is with pipelining. So in the way you do things without pipelining, the client will issue a new request only when the previous object has arrived. So the thing that you gain here in doing persistent without pipelining is you are reducing on the overhead of creating the initial TCP connection. You don't have to create a separate TCP connection for each object. Persistent with pipelining, on the other hand, as soon as the client realizes that it has a number of different objects to download from the server, it will send all the requests along without waiting for the previous request to be satisfied or fulfilled. So it will just send all the requests along and it will wait for all the objects to be downloaded on that same connection. So where do you gain here in the pipeline way of doing things? I'm sorry? Well, parallel downloads, and also in situations where your round trip time is large compared to the time it takes to transmit these objects. You see, if you do things without pipelining, then you have to wait at least 1 round trip time for each object. You send a request, you get the response back. That is 1 round trip time, assuming that the object is small enough, so that in 1 round trip time it's transmitted completely. Here, if all these objects are small enough, then everything can be transmitted in 1 round trip time. So if your server is far away as in terms of the round trip time, persistent with pipelining will give you significant performance advantages if you have a number of different objects to transmit. So it is doing things in parallel, or you can think that it's doing things sequentially, but it's not waiting for things to finish. Things get started sequentially. and they proceed in parallel. But you don't have to wait for any object to be completely downloaded before starting the other one. Yeah.
Yeah, well, sometimes the persistent HTTP is slower than the non-persistent because for the HTTP 1.0, the object is downloaded parallelly, but for over several connections.
Well, that's again a browser workaround, right?
I mean that in HTTP 1.0, and the server can send the data to the client over several connections parallelly at the same time, and in HTTP 1.1, it's not a situation. So maybe the HTTP 1.1 sometimes will transfer faster than the.
You're saying 1.0 will transmit faster.
Yeah.
So what you're saying is, suppose, so what is the bottleneck in that scenario? Why would 4 parallel connections send data faster than one connection which has 4 objects going?
I think the server can. That means that more of the resource of the server is provided to the client.
More of the server resources provided to the client. So in that scenario, your bottleneck is not the bandwidth, but the server resource.
Yeah.
Right? Because if your bottleneck is the bandwidth, then sending things split over in 4 connections or sending one large connection would amount to the same. Right? But if the bottleneck is the server CPU, then possibly doing things with HTTP 1.0 might work faster. But that will work faster for an individual user, assuming everyone else is using 1.1. Right? Suppose there are 10 users and all 10 start using 1.0. Then nobody is gaining. Right? You can only gain when you are the only one using 1.0 and everyone else is using 1.1. So if you have 10 users and all use 1.0, then this becomes like 40 virtual users. So even though you have a 4-way split, you are getting 1/40th of the resources of the server, and you lose the benefits of pipelining and persistent connection. On the other hand, if you have 10 users and only one uses 1.0, then you have a scenario where you have 13 virtual users. Right? 9 users are using 1.1, so they have one socket assigned to them. Now we have opened up parallel connections. So in this scenario, you might win. But if everyone starts doing it, nobody wins and everyone loses. So instead of turning this course into a game theory course, we will just sort of assume that using 1.1 benefits everyone. And it's in very rare situations that you should be using 1.0. Okay, so how does HTTP actually work? Well, like most protocols, HTTP is a sequence of requests and responses. An HTTP request message has three parts. One is the request line. In the request line, you send the command associated with the type of request that you are issuing to the web server. In the second part, you have header lines associated with the request. And then optionally, you have the body of a request message. So different kinds of request commands are get, post or head. And the general format is this. You have the request line where you have the method is get, post, head, followed by the URL, followed by the version of HTTP. So you have the method, the URL and the version. So the version is very important. So the server has to know what version of HTTP the client understands. So you can try this at home or when you log into, let's say you log into a cluster machine. You can do this interactively. You can type the command telnet www.cs.columbia.edu space 80. So what that does is it opens up a TCP socket between your client and the web server, the Columbia web server on port 80, which is running there waiting for connections. And if you can type these things out instead of get some page.html, just type get index.html, http 1.1 and some headers like this. And then you can repeat the process. You observe what happens and then repeat the process by just changing this portion to http 1.0. And you'll see the difference between persistent and non-persistent. If you type the http 1.0, the server will send you the index.html and your connection will get closed. If you do 1.1, the server will send index.html and then you'll see the server waiting for another command from you. If the command doesn't come, the connection will get closed. So this is the PDU or the protocol data unit for HTTP, similar to the DNS protocol data unit that we saw last lecture. So this is the request message. So get is the most commonly used request method, which is used for downloading information from a server. But the request message can also upload messages or information to the server, and there are two methods of doing it. There's the post method and the head method. So again, details of how these methods are implemented, you can look at the book, look at the slides. In HTTP 1.1, another method has been implemented, which is put. And in put, you can upload a file, and the file is in the entity body of the path specified in the entity body, and it is uploaded to the path which is specified in the URL field. So when we look at this HTTP request method, what you are uploading, the file that you want to upload, is part of the entity body. If your request message is a simple GET, then this entity body is usually blank because you are requesting information. You're not trying to send anything. But if you're using the put method, then the file that you're trying to put to the server is part of the entity body.
How efficient is the food method?
I'm sorry?
How efficient
What do you mean by efficient?
compared to FTP?
Well, both FTP and HTTP are using TCP underneath. So the efficiency of these methods is really defined by how TCP is behaving. When we get to the transport protocol section of the course, you'll see that the performance of TCP depends on the round trip time, the loss rate experienced. So at a high level, it doesn't make a difference whether you're using put or whether you're using FTP, because underneath both of them are using TCP. So if your file is large enough, then the minor overheads of TCP control messages, FTP control messages or HTTP control messages don't matter. What matters is what the performance TCP is getting out of the network. The HTTP response message looks fairly similar. So instead of the first line in the request message was the request line, what you were trying to request from the server. In the response message, the first line is the status line. What is the status of your request? Is the status, the most common status is the server will respond with a status code 200 OK, which means that your request was a valid request as far as the server is concerned. The server will send header lines similar to the request message, and then the response will be sent after the request message, after the header lines. Whatever HTML or object file that you requested is sent after the header lines. Yeah. Why is the connection closed? Right. 1.1 closes the connection if it doesn't receive requests for a certain period of time. I'm sorry? Well, I'm not. Let's see what the request was here. Yeah, okay. It was part of the request. And then there are other header lines, the current date, the server version, last modified, which is useful for caching purposes, which tells you when was this object last modified, the size of the object, the type of the object, and then the data. The response status code in the HTTP response format, there are a number of different status codes, some which are most frequently encountered, well, 200 OK and 404 not found, that we see all the time. There are other status codes like move permanently, bad request, version not supported. Suppose it's in your request line you say HTTP 2.5. You try to confuse the server will simply respond version not supported. So this tells you how you can try the HTTP protocol from a simple terminal by just telnetting to a particular web server. Yeah, you can try this one with HTTP 1.1 and 1.0, and you'll see the difference in the response. Now we come to this notion of using cookies. So most major websites use cookies. Cookies, we've all encountered cookies, we are all familiar with cookies. And the idea behind cookies is to introduce some notion of state in web transactions. So like I said earlier, HTTP itself is stateless. So your web server that is running is going to be stateless. But these cookies will artificially create a notion of state which is not really maintained by the web server itself, but it's maintained by a backend database. And these cookies are used to identify different users. And it's one more example of separating location from identity. Here the identity which is tied to a cookie is usually a PC or a workstation from which you are connecting to the website. But it need not be strictly tied to that. You can move your cookie files to different accounts, and your identity moves with the cookie files. Your identity is not tied to your location in terms of your IP address or the specific machine that you're connecting from. It's tied to the cookie file that you maintain. So what is the cookie architecture? Well, the cookie header line is present in both the request as well as response messages in any transaction. The cookie file is kept on the user's host machine, it's managed by the browser, and it's processed at the server end by a backend database. So why is this part important? Cookie header in the request and response lines of the client and the server. Yeah, because HTTP is stateless. So the server has no idea, and it will never keep a history of who's connecting. That state is maintained by these two components of the whole architecture. The browser and the server are not going to keep a history of who you are, when you last connected, what you last connected to. That whole history is kept by the backend database. So if the backend database doesn't work or doesn't function, it will not come in the way of at least HTTP functioning. And it doesn't increase the complexity of the server in any significant way. So HTTP server is still kept it stateless, but your identity is sent every time you send a request. Every time you send a request, your cookie header line is going to go with your request. So the server doesn't have to remember. So this is a typical creation and use of cookies. The first time a client connects to an HTTP server, it'll it'll send some request message, get me this particular URL. The server will send the response, and in the header line, there's going to be an additional header, set cookie to this particular value. So now what the server is going to do is, there will be some backend database in which an ID is created for this user, for this particular connection. So 1678 is the ID connected for this user. Now, the next time this user or the browser sends a request message to the server, the client in its header lines will send a cookie. The server will receive this cookie and will send the message across to the backend database that this particular client has reconnected. Do you want me to do anything with this cookie? So on Amazon, if you go and you have cookies enabled, the backend database will create a user-specific web page. It knows what you bought last time. It'll tell you, it'll advertise similar items. If you go on eBay, similar things happen. The backend database is creating a record of your history of what things you're interested in, what part of the website you browsed, and it also uses that history to create dynamic web pages tailored to your interests. And so the cookie specific actions are all being done here. So the server is remaining stateless. The state is being maintained and acted upon by the backend database. Yeah.
How are the cookies maintained on the client?
So the client, the browser will maintain a cookie file. So it will maintain a file which will have this table that for Amazon.com, my cookie is 1678. For eBay, the cookie is 8734. You'll have site-specific cookies, so site-specific identifiers. So what cookies can bring? Well, authorization, shopping carts that we have used, recommendations on sites like eBay, and then web email. When people thought of using the web for email, you needed this concept of having state or a session of a user. The basic HTTP architecture does not allow maintaining state or any notion of a session. That notion is created with HTTP by the server dynamically generating a cookie every time you log in. So every login will have a specific cookie associated with it. Which is difficult to guess using some sort of standard cryptographic techniques. And your session identity is maintained by the HTTP server by exchanging this cookie with every request and response. So no one else can get into your email account even by faking your IP address. Okay, now let's get to this notion of web caching or proxy servers. So how many of you have used a web cache or a proxy server? So you all know what a proxy server does. You have a basic understanding what a proxy server does. A proxy server is a server which is sitting in front of a client, and it will try to satisfy any HTTP request sent by a client. And the proxy server acts as both a client and a server. So suppose you're a client and you have set some machine as a proxy server, and you ask for a particular web page for this proxy server, www.cnn.com. Now, if this proxy server has that web page, it will immediately send you the response back. If it does not contain a copy of the web page, then it will go out to cnn.com. It will act as a web client. It will send a request, get the response, and then transmit it back. The advantage of this is once it has a copy of index.html for cnn.com, the next client that asks for it, it doesn't have to go out on the internet and face the internet bottleneck or face the internet round trip delays, and this page can be served really quickly. The basic idea of caches is to move the information as close as possible to a client to reduce latency, to reduce bandwidth related delays. Another idea of using caches is that it can reduce the load on the web server. Yeah.
Can you cache like websites like CNN.com, which are like changed every half an hour, 1 hour?
So you exploit the header messages of your response line to see if the copy of your web page, the thing that you have cached, is stale or is it fresh. So before giving the example, let me show you how it's implemented. So a conditional get is a standard HTTP request message, and it contains a header line which says if modified since. So caches also work on your local browser, on your local client. Often web pages come up very quickly because you have stored copies of the images associated with that web page. So what's happening there is your browser is going to send a request. If this object has been modified since, then send it back to me. The server will respond that this has not been modified in the last half an hour or 1 hour. So I'm not going to send you the object, I'll only send this status code, not modified. So this interaction will be quick, and you don't have to download a fresh copy.
Modified since time to the current time when the request is made.
No, modified since you want to send the time when you last downloaded a copy of that page. So you have a copy of the page which was modified whenever you downloaded, and you ask if that page has been downloaded since then or not. If it has been, send me a new copy. If not, just send me the status code. So this is the mechanism with which caches work, and proxies will do the same thing. They'll get a request message. They'll see what URL has been requested and what is the last version of the URL that they had. And servers in their headers can also set an expiry on the particular URL. So that's like a TTL. So I'm sending you a copy of index.html, but it's not going to be valid 15 minutes from now. The server tells that to the proxy client. Once the proxy client has this information, then 15 minutes later it'll go and simply fetch a new copy. Or on demand, after 15 minutes it'll go and fetch a new copy. So now let's look at the performance benefits of caching. So here you have an example where you have some institutional network. The institutional network is connected to the public internet using a 1.5 megabits per second access link. And then you have origin servers which are spread across the public internet, and requests from these browsers are arriving at the rate 15 per second. You assume that pipeline HTTP 1.1 is being used. So the delay from this router, the institutional router, to any server and back with the web page is 2 seconds. What is going to be the total delay faced by messages taking this route from the browser to the origin server to the back, to the origin server and back? Now, average object size is 100k bits. So that's the average size of the object that you're trying to download from the internet. You're generating requests at the rate 15 per second. So the amount of data that's being downloaded per second is 100k times 15, that's 1.5 megabits per second. So what is that data is flowing down to these client machines. What is the utilization in this institutional LAN? 1.5 megabits per second divided by the capacity of this LAN, which is 10 megabits per second. So utilization is roughly 15% or 15%. So we have seen how delay and utilization are related. So the curve looks something like this. When utilization is 1, the delay is going to explode. When the utilization is low, the delay is going to be minimal. So 15% utilization would be somewhere here. So the delay experienced in this part of the network is going to be very low because the utilization here is low. The delay experienced on this part of the network, on the other hand, is going to be very high because your access link is 1.5 megabits per second. Your data download rate is 1.5 megabits per second. So your utilization of that link is getting pushed to 1. So that link is getting congested because of heavy traffic. So queuing delays are going to rise on that link. So that part of the delay is going to rise. So the total delay would be the delay here plus the delay here on this link plus the delay on the public internet. So that's going to be 2 seconds, which is the delay of on the public internet, plus a delay maybe of minutes. Well, this is exaggerating it, but it can be significantly high. Even if the delay is not of the order of minutes, packets are going to get dropped if your utilization is 1, plus some delay here, which is of the order of milliseconds. So the dominant factor here is this minutes delay, which is happening here. So what are the options? How can you fix it? You want to reduce the delay on this link. One option is you can increase this link speed to 10 megabits per second. So the utilization here reduces to 15%, and the delay here also reduces. The other option is to use a cache. So this is the first option where we have increased the access link bandwidth and you have brought down the queuing delay on the access link to the order of milliseconds. Now suppose you install a cache on the LAN. So you have installed a server which is acting as a cache, and suppose the cache hit rate is 40%. So this server will contain 40% of the requests that are being generated. They are already here. So this server does not have to go out to the public internet, to the origin server, to get web pages. So 60% of the requests still have to go out, 40% of the requests are still satisfied, are going to be satisfied locally. So what that does is the utilization of this link now comes down to 60%. So you are at a much more manageable position in this curve. You're going to bring down the delay of this link by simply adding a cache. So you add a cache server, you bring down the delay on this link, you don't need to do any kind of upgrade, and your delay is going to come down again to 2 seconds plus whatever the milliseconds delay that you have. Yeah.
Just explain one thing. Just one before that. Yeah, I can understand how average request rate from institution browser to origin server is 50%.
So that's an assumption. Suppose the browsers are generating requests, 15 requests per second, and the average object size is 100K.
Multiply the object size by the average rate and divide the rate on the link by that. Right?
Yeah, so every second you are requesting 15 objects from the internet. The average size of each object is 100K.
Yeah.
So the average bandwidth that you need from the internet down to these clients is 1.5 megabits per second. So that's the assumption of the model. This is just to highlight what could happen. It's sort of showing you the worst case scenario where this link is completely congested. You can alleviate this congestion without increasing link bandwidth because there is a high degree of correlation of what the users here are requesting from the internet. Everyone sort of typically goes to CNN.com or ESPN.com. So there's a common interest across users, and what this does is it tries to exploit that.
So you actually do some kind of statistical counter before you implement a cache.
Cache design is a whole field altogether. How do you increase hit rates? What kind of replacement policies you use? So this idea of caching was taken one step further by companies that did content distribution networks or CDNs. So Akamai was the first company that introduced this concept of having CDNs. So what do CDNs do? The CDN providers, you can think of a CDN server as a cache server or a proxy server. The clients of a CDN node are going to be origin servers or content providers. So CNN.com is going to be a client of Akamai, which is a CDN provider. So CDN provider like Akamai will install CDN servers spread across the internet. everywhere it will have its own servers installed. There's going to be a CDN distribution node. So the origin server or CNN.com will generate some content. It will send that content to the CDN distribution node, and the distribution node then replicates this content across all its servers spread all over the internet. For instance, Colombia, the network in Colombia houses 5 to 10 Akamai nodes. So CDN nodes are running in our network, and when we go out on the web, we are using these CDN nodes all the time. So how do these CDN nodes work? So an example is you send a query to an origin server. So foo.com is the origin server, and you're sending a query. The origin server has, let's say, part of its content, like images, content which is not dynamic but fairly static. So in the sports.html web page, this origin server foo.com has some images. Now instead of housing those images locally at the origin server, what the origin server does is it replaces that URL with a CDN URL. So now it's saying that those images you don't need to get from me but from a CDN server. So when the browser passes that HTML, it will get references to these objects which do not reside on the origin server. These objects are still needed to recreate the web page or to create the web page as a browser. But now the browser knows that it has to go somewhere else to get these web pages. Yeah.
What's the benefit of this going away? If the origin server doesn't have the web page, then why would you have to establish an interconnection with a different server?
So we will come to the benefit. So step one, you get the base URL from the origin server, and then you get a bunch of objects that you need to get from the CDN server. So in step two, you're going to send a DNS query for this www.cdn.com. And in step 3, you contact the cdn.com machine and get the URL. The insight and all the benefit happens in step 2. So what has the origin server done? It has simply replaced the foo.com image URL with a cdn.com image URL. Now these CDN servers have CDN nodes replicated all over the internet. The question is, which node should you go to? Right? I mean, if you have CDN servers in South America, Europe, in Asia, if the change in URL forces you to fetch that image from a CDN server in Asia, you're not benefiting. But if somehow you go to the CDN server which resides at Colombia, then you'll get that object really fast. Your round trip delay is going to be low, and the bandwidth consumption over the internet is going to be low. You're going to use the local Colombian network, which the utilization of which is low. So how do you manage that? Well, what these CDNs do is they create a map of the internet which indicates distance from leaf ISPs or the end nodes and CDN nodes. So when a query arrives at this DNS server of a CDN node, it will look at the query and see where it's coming from. So if the query is coming from a node at Columbia, this map will tell the CDN server, okay, this query has come from Columbia. So it will resolve www.cdn.com to www.cdn-columbia.com or something like that to a machine which is local. If that query had arrived at that DNS server from a machine in Australia, it would have resolved that www.cdn.com to a machine which was in Australia. So the trick is what's happening in step number 2 here. This resolution is a smart resolution. cdn.com, which is the URL which that was given by the origin server, means thousands of different machines. So it can translate to thousands of different machines, and depending on where the query comes from, the resolution is done. So this DNS query is resolved in a smart manner, so you are sent to the closest server possible. Yeah.
DNS caching and all the other kind of mechanisms and distribution and stuff like that, how, are you hitting the authoritative DNS server every time, or how do you deal with distribution and that mapping? You know what I'm saying? Like, if DNS records are being distributed out, so say Columbia's DNS server or an ISP's DNS server,
Right.
is it just part of DNS that allows for that kind of mapping, or is it that automatically, no matter what, those requests have to go back to the authoritative server before they're...
Well, I mean, your first request went to the from the client went to your ISP DNS. That went to the CDN's DNS. Right? So the CDN knows that it has come from this ISP. So the reply that it sends would be a CDN node which is closest to this ISP. And the reply also has a time to live. So this ISP can only cache this reply for a certain amount of time. And CDNs, I mean, if you look at the Akamai architecture, it works at multiple levels. Different servers have different time to live for the resolution. So in reality, there is not one CDN node sitting at Columbia. There are 10 different or 15 different nodes sitting here. So what do you resolve this to? What the CDN companies also do is they're constantly monitoring the load on these CDN servers, and they send you to the best one currently available. And for that, the reply that is sent has TTL of the order of seconds. So by creating a small TTL, this cached entry is not retained for too long. And that enables the CDN servers or the CDNs to be very flexible and make the best possible use of the available resources. So not only do they send you to the closest server, they also send you to the least loaded server. And if one server crashes, then they can easily fix that. Yeah.
Can we combine CDNs with cache net proxy servers?
Can you combine
CDNs with cache net proxy servers?
What do you mean by combine?
As in, suppose in this case, instead of requesting an object from the CDN server, suppose we have a proxy server caching at the organization. So can we cache that object as well?
There's nothing stopping you from doing that. The only thing is that you should be getting a fresh copy of the object, not a stale copy.
So once you retrieve the page from the CDN server, what happens to the links that are there on the page? So those links, you go back to the original server or you go back to the CDN server?
Which links?
The links that are on that page.
So again, the links that are on that page,
Do they get directed to the CDN server? Or do
it depends whether that the links have been replicated on the CDN server or they remain on the origin server.
I mean, looks like getting very little.
No, you get a lot because a lot of the content is static content, things like images. And even web pages, they are, even the text is, although it's dynamically generated, but it's not generated very often. So, one thing is that the client gets a lot. Your latency is going to reduce. The origin server also gets a lot because its capacity is being replicated. The origin server, if it's a popular site, then it needs a large cluster of servers to serve all its customers. If you do it the CDN way, then most of the load is going to be distributed across this CDN network. And these CDN networks are highly over-provisioned, they can handle large loads. So if you are a website which is resource poor but content rich, it's popular but you don't have resources, then CDN servers can come in and give you their resources, and then it benefits both the server as well as the client.
Is the internet as a whole benefited? Because you're going to have the city and they have to map out all the signals and in constant communication with each other.
Yeah.
So the internet itself, I think, will take the burden of this idea.
No, not really, because you're pushing content as close to the clients as possible, right? So you've pushed one copy of the content here, and that gets replicated. So for all the clients of this ISP, you're not going out on the internet. You're going locally here. So even the traffic of the internet gets reduced. The control traffic is minuscule compared to the amount of web traffic that the CDN servers generate. In fact, I think Akamai, the CDN server, has a presence, or its servers, in 1100 different ISPs. So ISPs like Columbia or Tier 2 ISPs, 1100 different ISPs have Akamai servers, and they carry, at least according to their figures, 15% of the internet traffic at any time. So 15% of the traffic that is flowing is being served locally. That's a huge benefit. So the internet as a whole gets benefit by the CDN architecture. Yeah.
Each of these local servers has the content from all the sites that Akamai has.
Yeah.
That's a lot of data.
That's a lot of data, that's a lot of work. But they are making money, they're employing a lot of people. So, and the things that you need to do to make this happen, and to make this happen very efficiently, they use a lot of clever algorithms, performance techniques, a lot of good, stock Fox kind of theory papers have been translated into actual algorithms that are used by Akamai and other CDN companies. So CDNs, it's a very active research area. There are a lot of performance improvements that can be done, and it seems difficult when you just think about it, that all these websites, all their content has to be replicated, but you come up with clever ways to do that. You also keep a track of who's asking for what you need to replicate at what time scales. So beneath this simple idea, there's a very complicated architecture that makes it happen. Okay, let's stop here.